Hello everyone, this is Ustun from Cornell University. Today I will present accurate operation delay prediction for FPGA HLS using graph neural networks. This is a joint work with Chenhui Deng, Debjit Pal, Ziqing Li, and Professor Zir Zhang. With the increase in specialized hardware design complexity, high-level synthesis has been proposed as a way to improve design productivity by means of a higher level of abstraction and faster design cycles. With HLS, users can specify the hardware behavior in high-level languages such as C, C++, and HLS tools convert this high-level specification into RTL. There are many commercial HLS tools, some of which are Xilinx Vivado HLS and Intel I++ compiler, and there are academic HLS tools including LegUp and Bamboo. HLS has become a part of FPGA design flow, which consists of many other distinct and modular steps, including logic synthesis, placement, and routing, after which we get the final implementation. To accelerate design closure, it is crucial to have an accurate prediction of area and delay of final implementation during earlier design stages, because these predictions can be used as a quick feedback to control the behavior of each design step. For instance, delay predictions in HLS impact clock cycle boundaries established in the scheduling step. Furthermore, delay predictions allow users to quickly identify potential performance bottlenecks and modify their high-level implementation accordingly, or explore optimizations in HLS more effectively. However, area and delay predictions in early stages of the design flow can be quite inaccurate. Especially delay prediction in HLS is a very challenging problem because of the difference in the level of abstraction. Basically, HLS lacks awareness of downstream optimizations in logic and physical synthesis stages. Many HLS tools have very simple delay models, and therefore the delay values they report are inaccurate. They basically pre-characterize each operation in isolation and calculate the overall delay additively over these individual operations. And some HLS tools do not even provide delay predictions. Recently, ML-based approaches such as Quickest are being developed to bridge the gap between HLS predictions and actual implementation results. But these approaches are not very successful in modeling delay because the set of features they're using cannot truly capture design's topological structure. In other words, these models do not learn from the inherent structure of the design. To address lack of awareness of downstream optimizations, HLS can be made mapping aware. Some prior work introduced mapping awareness in HLS to improve scheduling outcomes, but they focus only on lookup table mapping. However, modern FPGA devices include a variety of dedicated blocks in addition to lookup tables. Let's see how operation mapping looks like for modern FPGA architectures. On the left, we have a data flow graph extracted from HLS intermediate representation, which includes the operations and their connectivities. On the right, we have a set of resources on the FPGA device. Lookup tables are the programmable logic resources, and there are also dedicated blocks such as DSPs and carry blocks for high-performance arithmetic computations. The question we are addressing is whether operation mapping patterns can be learned automatically. And now I will show two examples to motivate the need to learn operation mapping patterns for accurate delay prediction. These two examples will have the same data flow graph, but different mapping patterns. Here's the first example, where operations map onto the dedicated resources, which are DSP and carry blocks. This is an example where the additive delay model over individual operations would fail because we see that multiple operations can map to the same resource, which can be referred to as operation clustering. So, delay calculation should consider clustering of operations. Note that with this mapping pattern, critical path is from A to out, which passes through a DSP block and a carry chain. In this second example, mappings are different. And with the change in the mapping scheme, critical path now becomes D to out, which passes through two DSP blocks and the lock network. The point here is that mapping has a direct impact on timing. So we're proposing accurate operation delay prediction in HLS by first learning mapping of HLS operations onto device resources using graph neural networks, and then characterizing delay in HLS based on these learned mapping patterns, which leads to 72% improvement in HLS operation delay prediction. One of our targets is learning DSP mapping patterns. DSP blocks are widely used for implementing high-performance complex functions with multiplication operations. Typical applications are signal processing, medical imaging, machine learning, and media compression. Matching HLS subgraphs with DSP blocks is a challenging problem due to hard-to-predict optimizations that take place in logic synthesis. For that reason, commercial tools typically follow hard-coded rules developed by a group of engineers, which is a labor-intensive process. The figure is an example where 2 addition and one multiplication operation together map onto a DSP block, and the corresponding data path is highlighted in orange. Data path of DSP blocks are highly configurable, which means that there are so many subgraphs that can map to a DSP block. And our goal is to learn mapping patterns using machine learning techniques, and by doing so, eliminating the labor-intensive process of building mapping rules by HLS developers. We also target other clusters, which are realized by chaining carry blocks that exist in lookup tables. These dedicated carry logic helps speed up arithmetic operations. HLS tools fail to identify error clusters with more than 2 addition operations, contributing to the inaccuracy of delay prediction in HLS. In the figure, cluster identified by the HLS tool is highlighted in red, whereas the actual cluster in the post-synthesis netlist is highlighted in green. Therefore, we also propose to learn error clusters using machine learning techniques. There are many well-established machine learning models for learning representations from complex data, such as CNNs and RNNs. These models apply to regular data patterns or sequences of data. Graphs, on the other hand, are non-Euclidean data types. They are highly irregular, and therefore, it is inefficient to perform manual feature engineering on them. There has been an increasing interest on learning representations in graph-structured data. These methods, so-called graph learning, aim to learn low-dimensional representations of graph data. And among these, neighborhood aggregation methods fit well for our problem because we are interested in inferring local mapping patterns in a neighborhood around HLS operations. We formulate graph learning techniques on data flow graphs to learn mapping patterns based on both data flow graph structure and operation features. To be able to realize that, we extract the correlation between HLS operations and netlist operations. And our flow is as follows. From a set of microbenchmarks, our tool extracts the data flow graphs from HLS IR and correlates the operations with the netlist objects after technology mapping. Based on these correlations, actual mapping patterns are extracted. Then, data flow graph structure, node features, and the ground truth, which are actual mapping patterns, are used to train our GNN model. Once the model is trained, we can infer mapping patterns and characterize delay for any given data flow graph. Let's go through the data collection process in our framework. First, we generated microbenchmarks to train GNN models on. For each microbenchmark, we set the total number of operations to 20, and in order to have various subgraph structures among these microbenchmarks, we sweep the number of multiplication operations from 4 to 8 and the number of inputs from 8 to 12. Below is a tiny example with 3 input arguments and 3 operations. Corresponding high-level description generated in C is given on the right. As for training the GNN model, for each microbenchmark, we need the graph structure information, node features, and actual mapping patterns as the ground truth. Graph structure is represented as an adjacency matrix from which we can infer node connectivities. Node features are the additional information we have about the operations, which are operation type and bit width. These features are aggregated in small neighborhoods to learn embeddings of nodes. Finally, ground truth is extracted by correlating HLS operations with post-mapping netlist objects. If you might remember the data paths in a DSP block, this ground truth extraction is a challenging process. It can be difficult even with manual analysis, and we built an automated flow doing this without any manual intervention. RGN Model DSage is an improvement over GraphSage, which is an open source framework for inductive graph learning. GraphSage learns node embeddings inductively so that when new nodes are introduced to the network, the model does not need to be retrained. So, a pre-trained GNN model can directly be applied to unseen graphs without retraining. This is achieved by embedding generation methodology. Given graph structure and node features, at each GNN layer, the model first aggregates neighbor nodes information through parameterized functions, and then feeds the aggregated information through a fully connected layer to update node embeddings from the previous GNN layer. At the end of the embedding generation stage, we have node embeddings as functions of aggregator parameters and weight matrices from the fully connected layer. The next task is to learn these parameters by first defining a loss function, which ensures that similar nodes in the original graph map to nearby vectors in the embedding space. After this final stage, where model parameters are tuned to optimize the loss function, we obtain the node embeddings. Note that GraphSage does not distinguish predecessor nodes from successor nodes. This is a drawback, especially for DSP mapping, because the model cannot distinguish pre-adders from post-adders. Our model DSage, on the other hand, supports directed graphs and can distinguish between pre-adder and post-adder, leading to 17% better accuracy in predicting DSP mapping and 1.7x faster convergence during training. Now let's see DSage in action. Given data flow graphs with node features, the model aggregates information from predecessor nodes and successor nodes separately, and then updates node embeddings from previous GNN layers. At the end of this phase, we obtain node embedding functions. The second step is to learn node embeddings by performing supervised learning on node embedding functions. At the end of this phase, we can infer mapping patterns of HLS operations. Here are our results on learning operation mapping. In our experiments, the target device is Virtex UltraScale Plus. Here, the problem is a binary node classification problem where nodes are labeled depending on the type of resource that they map to. For example, the addition operation here is labeled 1 if it maps to DSP blocks and 0 otherwise. These results show how Vivada HLS performs in this classification task. F1 score is a measure of classification model accuracy, and it is widely used especially for unbalanced data. Our goal is to improve the F1 score. At the bottom, we have the results from our DSage model. We achieved 12% improvement in the F1 score compared to the HLS tool. To test the generalizability of DSage, we train our model on microbenchmarks and test on the given designs targeting 250 MHz, some of which are from Max3. We observe a 47% improvement in F1 score compared to the HLS tool. When node classification is applied to predicting carry chain mapping, we observe 3x improvement compared to the HLS tool. Here, a node is labeled 1 if it maps to a carry chain and 0 otherwise. So far, we automated learning DSP and carry chain mapping of arithmetic operations using graph neural networks. But if we think about delay characterization in more detail, we realize that node labels are not sufficient to infer timing. Here's an example. In this piece of data flow graph, if all operations are predicted to map to DSP blocks, we do not know whether operation 2 is clustered with operation 0 or operation 1. And this has a direct impact on timing because if node 2 gets clustered with node 0, that means operation 1 belongs to another DSP block. So delay from B to C, which crosses 2 DSP blocks, is higher than the delay from A to C, which crosses 1 DSP block. With this in mind, we formulated the second learning phase of our problem, which is binary edge classification. Here, edges are abstract in the sense that they represent whether the nodes that belong to an edge are clustered or not. In other words, an edge is labeled 1 if its nodes are clustered into the same device resource. The node labels produced by the previous node classification task becomes an additional node feature for this new edge classification task. Now we can see that HLS accuracy on this task is lower than the previous node classification task, which means that HLS tool does not capture many clustering patterns. Our approach, on the other hand, achieves a 28% improvement in the F1 score compared to the HLS tool. To test generalizability of DSH, we train our model on microbenchmarks and test on the given designs as before. We observe a 69% improvement in F1 score compared to the HLS tool. When edge classification is applied to predicting error clusters, we observe 5x improvement compared to the HLS tool. The score of Vivado HLS is very low because it doesn't identify error clusters with more than 2 addition operations, whereas our model, DSH, can identify error clusters beyond 2 others. We also extended our model to pipelined operations. We did so by further incorporating scheduling information from the HLS tool. Scheduling information is necessary because first, DSP blocks can be pipelined through their input, output, and pipeline registers, and this will impact mapping of operations onto DSP blocks. As for error clusters, pipelining may designate cluster boundaries. For example, these 2 adders that are assigned to different clock cycles will not be mapped to the same carry chain. We show that DSH performs better than HLS in both operation mapping and operation clustering tasks for both microbenchmarks and realistic designs, targeting frequency values from 250 to 400 MHz on a Virtex UltraScale Plus device. After learning operation mapping and clustering patterns using graph neural networks, we perform mapping-aware delay characterization for HLS. First, we have the histogram of HLS tool's predictions, x-axis showing the percentage error of prediction and y-axis showing the number of designs for each error range. For most of the designs, error in delay estimation is more than 60%, and the maximum observed error is 143%. Here are our DSH-based results. Histogram is shifted towards lower error percentages. For almost all designs, error is less than 60%, and the maximum observed error is 88%. At the bottom, we plot estimated logic delay versus actual logic delay. We see that HLS predictions deviate from the linear line, which refers to reduced accuracy. DSH-based data points, on the other hand, align better with the linear line, and we achieve 72% error reduction compared to the HLS tool. On the right, we compare more approaches on both microbenchmarks and realistic designs with respect to both logic delay and data path delay. Approaches leveraging our model DSH perform better than their baseline for both delay categories. As illustrated also in the plots, HLS plus DSH leads to lower error compared to HLS tool alone, and quickest plus DSH leads to lower error compared to quickest alone. In conclusion, we propose a new approach based on graph neural networks that learns operation mapping patterns in HLS and leverages these learned patterns to perform accurate operation delay prediction for HLS. Thank you for listening.